Okay, let's go ahead and get started. So I'm handing out the next problem set, which will be due next Tuesday. Just as a reminder, the problem set due tomorrow is a little on the long side, so I recommend starting soon if you have not started already. This next problem set, I think, the one that I'm handing out, is not quite as long, so that hopefully shouldn't be too much of an obstacle. So this week is one of my favorite, possibly my favorite week in the lectures this semester, because this week we're going to do the three classic tests of general relativity. So we will start by doing those three tests that were proposed by Einstein in the very beginning of the 20th century, one of which was solved within the first year of the subject of general relativity, the next of which was tested in the next few years, and the third of which was verified only some decades later. So the starting point for our discussion of the experimental tests of general relativity will be the Schwarzschild solution, which is the solution of the equations of motion of general relativity that we derived last time. So let me just write down the solution for you. So the metric that we are considering is the metric of general relativity in the presence of a static, spherically symmetric object. So this metric is static, so there is a t-coordinate, and because the metric is static, all of the components of the metric can be written such that they are independent of the coordinate t. There is also a radial coordinate r, which is somewhat similar to the radial coordinate in flat space. And there is a rotational symmetry, which we use to write the metric in a form so that it has the usual metric of a two-sphere sitting inside it. So just to summarize, we have a time direction, a radial direction, and a spherical pair of directions. So out at infinity, when r goes to infinity, this reduces to the usual metric on flat Minkowski space in spherical coordinates. It's got that dr squared plus r squared d omega squared piece. But as r gets smaller, the geometry is curved in some way, which is encapsulated in those two prefactors proportional to 1 minus capital R over the radial coordinate and its inverse. And here, this parameter r is a parameter with dimensions of length that parametrizes the solution, and it is known as the Schwarzschild radius, and it is proportional to the mass of the object. So if you, for example, wanted to find the metric in the solar system due to the curvature of the sun, then in the approximation where you can treat the sun as a static object which is not rotating, and where one can neglect the gravitational field due to the other planets in the solar system, this is it. This is the metric of the solar system. And so two of the three classic tests of general relativity are tests of solar system physics. The first test is a test of the effects of general relativity as a modification of the planetary orbits. And the second is a test of the motion of light as it passes near the sun. And so it is that first test that we are going to focus on today. So what we would like to understand is what effects the theory of general relativity will have on the motion of the planets going around the sun. So in particular, what we would like to study are the geodesics in the Schwarzschild geometry, which will describe the motion of objects moving in the presence of the gravitational field due to the mass located at r equals 0 in these coordinates, which we could take to be the sun. Or, if we were interested in studying the effects of general relativity on satellites, moving around the Earth, which is also an important subject, then we would work in the approximation where the Earth is a static spherically symmetric object. And we would use this metric to describe the satellites orbiting around the Earth as geodesics in this geometry. So we wish to study geodesics in the Schwarzschild geometry. And those geodesics will tell the story of the orbits of the planets, for example, in their full glory in the theory of general relativity. And we will see, in fact, that in many ways, the modifications from Newtonian gravity are rather simple and can be understood completely explicitly and very, very easily by studying the motion of geodesics in this geometry. And I remind you, as I did last time, that the value of R for normal everyday solar system objects is absolutely tiny. So, for example, for the sun, if you just plug in the mass of the sun in this formula for the Schwarzschild radius, then you'll find that it's of order a couple kilometers, which of course is very, very small compared to the actual mass of the sun. So this metric is a reliable approximation for the geometry around the sun only outside of the exterior of the sun. So when using this to answer questions about solar system physics, we should keep in mind that this can only be used when R is much bigger than the Schwarzschild radius, in particular when it's outside of the interior of the sun. Only later, maybe starting at the end of this week and next week, will we begin considering more exotic objects whose radius is of order or small compared to the Schwarzschild radius. And in that case, those objects known as black holes, of course, have a very interesting physics. But today, we're going to restrict ourselves to the classic tests of general relativity, which, from a certain point of view, can be thought of as tests of the Schwarzschild geometry. Now, of course, in the many decades since the discovery of general relativity, there have been many other tests of general relativity which go beyond just tests of the Schwarzschild solution. But I think it's fair to say that at least for the first 50 or 60 years of the theory of general relativity, the only real tests of the theory were tests of the Schwarzschild geometry. So I'm just going to dive in now and begin the study of geodesics in the Schwarzschild geometry. But before I do so, let me pause and see if there are any questions on the Schwarzschild geometry or what we did last time. No questions? This is actually a pretty good showing for a day when there's a snowstorm. But, no questions? Good. Okay. So, as we know, a massive object moving in the presence of gravity, but no other external forces, will move on a time-like geodesic. And this geodesic is parameterized by four functions. So the four coordinates are t, r, theta, and phi. And we will introduce a parameter lambda, which will label points on that geodesic. And the geodesic is given by some set of four functions. And the geodesic equations give us second-order differential equations, which allow us to determine t, r, theta, and phi as functions of lambda by solving those four coupled second-order differential equations. Now, in the Schwarzschild background, these geodesic equations are not terribly complicated. You just need to compute the Christoffel symbols for the Schwarzschild metric, and then just go ahead and start turning the crank and solving those differential equations. But in physics, it's always good to be as lazy as possible. And so what we will do today is we will use a variety of tricks that will allow us to never actually have to write down those geodesic equations. And in particular, I will use the fact that because the Schwarzschild geometry is very symmetric, there are lots of conserved quantities. We introduced the notion of conserved quantities in general relativity last week, and now I will go ahead and use the knowledge that we gained in our study of symmetries to write down these equations of motion using these conserved quantities and never having to actually compute any Christoffel symbols. Do not worry, however. You will have plenty of opportunities to compute Christoffel symbols for Schwarzschild and other geometries, but I think it's always good to be as lazy as possible, although no lazier, at least when I'm giving the lecture. Okay, so what does it mean that we have a time-like geodesic? Well, that means that if you compute ds by d lambda, which is the change in the proper length along the geodesic with respect to the quantity lambda, then that is going to be a time-like quantity, meaning that its square will be negative. So what is this guy? This is just g mu nu, x dot nu, where g mu nu is the Schwarzschild metric, and that will be a negative number. And what I will do is consider an affine parameter where that quantity is, by definition, equal to minus 1. So I will just take my coordinate lambda to be such that ds by d lambda is equal to the square root of minus 1. So ds by d lambda squared is equal to minus 1. Or, in other words, I am taking lambda to be the proper time as measured by an observer who is sitting on this geodesic. Remember that the proper time is tau is related to the proper distance s by a factor of I. So saying that ds by d lambda squared is minus 1 is the same as saying tau is equal to lambda, where tau is the proper time. Okay. Now, in that case, the geodesic equation is rather simple. It's x double dot plus a Christoffel symbol times x dot squared is equal to 0. But rather than going through the whole rigmarole of solving that geodesic equation, what I would like to do is use the fact that the killing vectors will allow me to construct conserved quantities that are integrals of this geodesic equation, and so I'll never need to compute those Christoffel symbols explicitly. So the first thing that I would like to consider is I would just like to consider geodesics which are confined to the plane where theta is equal to 0. So that is the equatorial plane of the sphere. So remember the sphere, so I'll just write down the metric again for you. So we had minus 1 minus r over r dt squared plus 1 minus r over r inverse dr squared plus r squared times the metric on the sphere So you can see by looking at the metric on the sphere there that when theta is equal to pi over 2 or minus pi over 2, the coefficient of d phi shrinks to 0. That's just a sign that the north and the south pole of the sphere are at theta equals plus and minus pi over 2. And the equator of the sphere is theta equals to 0. And in fact, if you were to go through and study the geodesic equations very carefully, you would see that just as in the case of Newtonian gravity, you could always restrict your attention just to those geodesics which lie in the theta equals 0 plane. So hopefully you remember from your study of the two-body problem and the Kepler problem in mechanics that the motion of an object subject to a central force potential will always lie in a plane. The same is true in general relativity, as you could easily show if you wrote down the theta geodesic equation. And so it will suffice to consider those geodesics which lie in a plane, which in this case I'm taking to be the plane where theta is equal to 0. Any questions on that? It's an enjoyable exercise to go through and check that this is the case by writing out the geodesic equation for theta double dot explicitly and showing that theta can consistently be set equal to 0. But I won't bother to do so, since it's exactly the same thing that happens in Newtonian gravity when you're considering the Kepler problem. Okay. Now, when theta is set equal to 0, there are still two obvious killing vectors, meaning two obvious symmetries associated with this metric. So this metric still has a time translation and a rotation symmetry, which are generated by the killing vectors d by dt and d by d phi. Here I'm using our slick notation for a vector as a differential operator. So when I say the vector d by dt, I mean the vector whose components in this coordinate system are 1, 0, 0, 0. And when I say d by d phi, I mean the vector whose components in this coordinate system are 0 except in the phi direction where they're equal to 1. And the fact that this metric has these symmetries is reflected by the fact that the components of the metric are independent of t and independent of phi. And as we saw last week, the fact that there are these symmetries means that there will be two conserved quantities. So that means that there will be two quantities which we can call E and L, which are independent of lambda. So associated to the geodesic, which is given by these four coordinates x mu of lambda, we can construct conserved quantities associated with the killing vectors that are conserved as a function of lambda. So in particular, if you have a geodesic, so given a geodesic, x mu of lambda, and a killing vector, k mu, then if you use a affine parameter, the quantity x dot mu contracted with k mu is independent of lambda. This is Noether's theorem in a curved spacetime. We encountered it last week when we studied symmetries, and you're going to prove this using the geodesic equation on your problem set, which is due tomorrow. Hopefully you've already proven it. But if you haven't, you will do it within the next 24 hours. 26 hours. 27 and a half hours. 26 and a half hours. 26 hours and 35 minutes. Why would I do that? Would you guys really prefer, is it really substantially easier to have it do at 5? Everyone? Yeah. Let's say, okay, 5. Let's say 5. Would that make everyone happy? Yeah. Okay. Will it prevent me from getting a lot of extension request emails at 11 a.m. tomorrow? Okay, we'll have the problem set due at 5 tomorrow. Does that make everyone happy? Okay. problem set due at, I guess nothing can make you happy. Okay, less miserable. Okay, problem set due at 5 tomorrow. Don't say I never do anything for you. I can't have it due at midnight because the building's locked at some point, and it presents. I could have Kesha picked up, yes. No, but no, the building's locked. I shouldn't have them do after the building. They lock the building at some random time in the evening, and so let's say 5 p.m. Okay, that sounds good. Okay, so there's a quantity which is the contraction of the tangent vector of the geodesic with the killing vector, and that quantity will be independent of lambda. So it's an integral of motion. And this is proven by combining the geodesic equation with the equation for the killing vector. So here we have a geodesic equation and we have a killing vector. So let's construct the conserved quantities. Now, I have given auspicious names to these conserved quantities because the conserved quantity associated with time translation invariance is usually called energy, so I've called it E here. And the conserved quantity associated with rotations is usually called angular momentum, so I have called it L. Okay, so let's go ahead and compute these guys. So E, for time translation invariance, our killing vector is d by dt, meaning that k mu is equal to 1, 0, 0, 0. So what is k lower mu? Well, we need to lower that vector index. So let me scroll up, and you can look at the metric up here. So what is the coefficient of dt squared? That's gtt with 2 lower indices. That's minus 1 minus the Schwarzschild radius over r. So k lower mu is the vector whose first component is minus 1 minus big R over R with zeros for the rest of the components. So that means that the conserved energy is going to be the contraction of k mu with x mu dot. For the sake of conventions and to compare with our Newtonian notion of energy, I'm going to put a minus sign right there. So of course, if k mu x dot mu is independent of lambda, so is minus k mu x dot mu. So that minus sign is just a convention that I introduce for convenience. And then we can just go ahead and plug this in. What is this? This is 1 minus big R over little r times t dot. So that means that I can solve explicitly for t dot in terms of r. T dot, which is dt by d lambda, is equal to 1 minus big R over little r times a constant. And that's just some constant of motion, which will appear as an integration constant if I were to write out the geodesic equations explicitly as second-order differential equations and start integrating them. Note that if R is very large, then I can neglect that second term, and I just have t dot is equal to a constant. And that's just the usual equation for a straight line in Minkowski space, right? It says that all of the x mu dots will be constants. And so we see now that this is modified in a simple way in the Schwarzschild geometry. Yes? Oh, inverse. Thank you. That's why everyone's looking at me in a strange way. Okay, good. Okay, let's now compute the conserved angular momentum. So k mu, in this case, is the vector which has a 1 in the phi direction. So let's go ahead and lower that index. Let me now just scroll up here, and so we can look at this geometry. What is g phi phi? That's r squared times cosine squared phi. Sorry, r squared times cosine squared theta. Theta is equal to 0, so cosine theta is equal to 1. So g phi phi is just r squared. So this is the vector 0, 0. This is the one form with components 0, 0, 0, r squared. So the conserved angular momentum will be r squared times phi dot. Hopefully, those of you who have not completely forgotten the Kepler problem in mechanics will see that that formula is somewhat familiar. It's exactly the usual formula for the angular momentum in the z direction of a Keplerian orbit which lies in the xy plane. Is that hopefully familiar to some of you at least? And it allows you to solve for phi dot in terms of r. Phi dot will be L over r squared, where L, like E, is a constant of motion. Okay. So I have now used two nice little tricks. I've used the conservation of energy and angular momentum to write down equations for t dot and phi dot. The third trick that I would like to use is the fact that we are using an affine parameter. What does that mean? That means that ds by d lambda squared, which is equal to g mu nu, x dot nu, is equal to minus 1. So let's go ahead and write out that equation explicitly. That says that minus 1 is equal to minus 1 minus big R over little r t dot squared plus 1 minus big R over little r dot squared, inverse times r dot squared, plus r squared times theta dot squared, which is equal to 0, because we're in the plane where theta is equal to 0, times cosine squared theta, phi dot squared, which is just phi dot squared, since theta is equal to 0. So we see that the equation for the affine parameter is a first-order differential equation for r, t, and phi. But we have just used Noether's theorem to show that r dot and phi dot can be solved for in terms of r using constants of motion. So in particular, phi dot is L over r squared, and t dot is 1 minus big R over little r times E. So let's just go ahead and plug those into this equation. What do we get? We get minus 1 is equal to minus 1 minus big R over little r inverse times E, because t dot, sorry, there's a square there. Sorry about that. That's because it's dt squared. We get 1 minus big R over little r times E, plus 1 minus r over little r inverse times r dot squared, plus L squared over r squared. And this is a first-order differential equation for r as a function of lambda. E squared, thank you. So what we can do then is solve for r dot in terms of r. And what I would now like to do is solve for r dot in terms of r, and I would like to write it in a suggestive form. So r dot can be solved for in terms of r using this equation. And in particular, this is an equation for r dot squared. And in particular, it's an equation for 1/2 r dot squared. And I can write this equation as 1/2 r dot squared plus a function of r that I will call v effective is equal to a constant. So let's stare at this equation for a second. So how would you rewrite this upper equation in terms of that lower equation? Well, you multiply everything through by 1 minus big R over little r to isolate this r dot squared term. Maybe you multiply it by a half, and you see that that will be equal to a constant, E hat, which is equal to 1/2 E squared. And the effective potential, V effective, is just some function of R. So what is that? Well, we multiply through by 1 minus big R over little r, and we also need to multiply by 1/2 to make this equation look nice. So what is V effective? Well, we get 1/2 times 1 minus big R over little r plus L squared over r squared times 1 minus big R over little r. Or, writing this out, we get 1/2 minus big R over 2r plus L squared over 2r squared minus r L squared over 2r cubed. Is it clear what I've done here? So what have we seen? What we have seen is that the geodesic equation for a observer moving on a time-like geodesic in the Schwarzschild geometry is just that of a particle moving in a potential. This equation here is the equation for the conservation of energy of a particle moving in a potential. So the geodesic equation is just the equation for a particle moving in a one-dimensional potential. And that equation is the conservation of energy. 1/2 r dot squared plus some effective potential is equal to a constant, where the effective is the sum of 4 terms. I'll just rewrite it here. 1/2 minus big R over 2r plus L squared over 2r squared minus r over L squared 2r cubed. So it's now completely straightforward to understand what the solutions look like. And in fact, you'll remember that when you're studying standard particle mechanics, it doesn't really matter if you shift your potential by a constant. That doesn't affect any of the solutions to the equations of motion. So we could even just neglect that constant piece as far as studying solutions to the equations of motion. And so we see that we just have a particle moving in a potential with 3 terms. And hopefully this idea that a particle, that the orbits of the planets around the sun, for example, can be written in terms of the Kepler problem as a particle moving in the presence of a one-dimensional effective potential is not entirely unfamiliar. So let me remind you of Newtonian gravity. So in Newtonian gravity, you have the identical situation. And what is the effective potential in Newtonian gravity? Well, it's minus gm over r. That is the usual form for the gravitational potential, which, using the relationship between the Schwarzschild radius and the mass, is just minus big R over 2r. And then there's an effective angular momentum term, which leads to the famous angular momentum barrier, which arises if you study the effective potential of an object with angular momentum. And what is that? That's L squared over 2r squared. So we see that the only effect of general relativity in this case is an additional term that goes like 1 over r cubed that appears in the effective potential. So in order to understand the effect of general relativity on, for example, the orbits of the planets or the orbits of satellites, in this approximation, it's nothing more or less than just adding an additional term to the effective potential. You know, last year when I taught mechanics, I certainly could have assigned this as a problem on a problem set. Investigate the effects of the addition of this extra term in the effective potential of the Kepler problem. It would have been a completely straightforward, but probably slightly unfair problem for me to assign. So, in order to, before we begin discussing the relativistic effects of orbits, let me just remind you of a few features of Newtonian gravity, so we'll have something to compare our relativistic answers to. So, in Newtonian gravity, for all values of L, so let me just plot this function for you, actually. What does it look like? At small values of r, it diverges like 1 over r squared. It has a minimum at some value of r, and then it goes to 0 like minus 1 over r at large radius. So this is v as a function of r. And so immediately you can see by looking at this that for all values of L, there is a stable circular orbit at some value of r, which, if you went ahead and solved for it, would be 2L squared over r. Secondly, the orbits are conic sections. So, for example, the orbits of planets are ellipses or circles, which all come back to each other and repeat ad infinitum. And there is an angular momentum barrier which repels us from the origin at r equals 0. And finally, one additional feature of this potential is that for all values of r, there is a stable circular orbit. For any value of radius between 0 and infinity, you could always find a value of the angular momentum which would make that the stable circular orbit. And we will see that none of these properties are true once general relativistic effects are included. So let's now compare this to Einstein gravity. So in Einstein gravity, I'll just give myself some room here. The first two terms in the effective potential are identical. We have a 1 over r force, which is the standard Newtonian gravitational force, gravitational potential. We have an angular momentum barrier, and we have a magical new term, which is the new relativistic term, which was proportional to 1 over r cubed. And in this class, we usually set c equals to 1, but just for the sake of instruction, let me just show you where the powers of C belong. So if we no longer use units where C equals 1, then there would be a power of 1 over C squared there. And so you can see explicitly that this is a relativistic effect. C is a very, very large number. And so for everyday sorts of problems, this third term will be very, very small, simply because C is so large. In order for that third term to be sizable, either the radius r needs to be close to the Schwarzschild radius, or the velocity needs to be of order the speed of light. Neither of those are true, of course, for planetary orbits or for the orbits of satellites around the Earth, so that means that relativistic effects will be small. But in some cases, they are measurable and occasionally even important. Well, they're always important, but occasionally they're even of order 1. So let's just graph this potential and spend some time thinking about it. So the first thing that you notice is that instead of diverging to plus infinity as r goes to 0, this effective potential now goes to minus infinity as r goes to 0. Because as r goes to 0, that minus 1 over r cubed term dominates. And so what this potential will look like is it'll go like minus 1 over r cubed for a while. And then the 1 over r squared term, which is the angular momentum barrier, will take over. And then, finally, at very large radius, the usual 1 over r behavior will take over. So this is what v will look like as a function of r. Now, I have assumed in drawing this that L is sufficiently large. So, of course, if L is very, very small, then this middle term will always be negligible compared to the first two terms. So I've assumed here in particular that L is larger than the square root of 3 times r. You can check, you could just check by computing dv by dr that in order for dv by dr to have two zeros, namely for this v to have two turning points, L needs to be bigger than root 3r. So you can immediately see that there are some very important qualitative differences with the Newtonian case. Yes?
What if it's not?
What if L is less than root 3r?
Yeah.
We'll discuss that in a second. So if L is bigger than root 3r, then we have a stable circular orbit, as usual. We also have an unstable circular orbit. So let me call that RC. We also have an unstable circular orbit at a place that I will call R critical. And it's straightforward to go ahead and solve for RC and R critical. RC is L squared plus, so you just take the derivative of V and set it equal to 0, you get a quadratic equation for R, whose solution is L squared plus L to the fourth minus 3 R squared L squared over R for RC, and the other solution of that quadratic equation gives you the other turning point of this trajectory, which we called R crit. And you can immediately see that when L is equal to the square root of 3 times R, those two turning points coalesce, and the behavior of the potential will change. So, we see that, again, so as in the Newtonian case, we have stable circular orbits at RC. But one thing that you can see by looking at this equation for RC is that this is always less than 2L squared over R, which was the location of the circular orbit in the case of Newtonian gravity. So these circular orbits will be slightly closer to the Sun or to the center of the Schwarzschild solution at R equals 0. But more importantly, there is a limit on how close these stable circular orbits can be to R equals 0. In particular, let's look at this RC in the limit where L is large. So as L goes to infinity, how does RC look? Sorry, that's R crit. Oh, I see. Okay. The other thing to notice is that L had to be larger than root 3 times R. And so what that means is that RC is always bigger than 3 times R. So that means that there are stable circular orbits only at radius which is 3 times the Schwarzschild radius or larger. So only far from small values of R. So they're stable circular orbits only for sufficiently large radius. Second, of course, there are unstable circular orbits. At the value of radius R crit. And in fact, as L runs from root 3R up to infinity, R crit will run between 3/2 the Schwarzschild radius and 3 times the Schwarzschild radius. So you can actually see that the radius of the unstable circular orbit is always relatively close to the Schwarzschild radius. So as when L is equal to root 3R, of course, R crit is equal to 3R, just like the radius of the circular orbit. And as L goes to infinity, you could go ahead and compute R crit by Taylor expanding the square root. So what is it? You get L squared over R times 1 minus the square root of 1 minus 3 R squared over L squared. So you could then Taylor expand the square root, and you get 1 minus 1 plus 1/2 times 3 R squared over L squared. So you just get 3/2 R. And finally, of course, and this is perhaps the most important point, the orbits will not be conic sections. So remember that the fact that orbits in Newtonian gravity are conic sections is very special to the fact that you have a 1 over r squared force in Newtonian gravity and a 1 over r potential. Here we have some corrections to that 1 over r potential. which will mean that the orbits will not be conic sections, so they won't be parabolas, for example. And in particular, the orbits will not close on themselves. So, for example, if you were to study, the orbit of Mercury around the Sun, what you would find is that the orbit would be very close to a parabola. Sorry, not parabola, ellipse. Why am I saying parabola? The orbit of Mercury would be very close to an ellipse, but it wouldn't exactly be an ellipse. And instead, the orbit would change gradually as time went on, so that eventually the orbit might look like this. Sorry, I'm not an artist. So that gradually the orbit would, as they say, precess around the Sun. And indeed, the precession of the orbit of Mercury had been observed many, many decades before the advent of general relativity. And the first success of general relativity was the description of the precession of the orbit of Mercury. The precession of the orbit of Mercury was one of those outstanding mysteries in the physics in 19th century astronomy, which was more or less, I don't want to say ignored, but unappreciated for several decades until Einstein realized that his theory of general relativity, in fact, provided a precise explanation for this precession. And this is something that we'll compute explicitly. Before we do so, however, I just want to notice and emphasize that when L is less than root 3 times R, what does the potential look like? Well, remember that the potential was two negative terms. There was a minus 1 over R and a minus 1 over R cubed term, and then a plus 1 over R squared term that came from the L squared over R squared term. So if L is sufficiently small, the potential is strictly monotonic as a function of R, and so there are no stable orbits. So if you have an object without enough angular momentum, so in Newtonian gravity, if an object has a very small amount of angular momentum, then it will eventually end up in some orbit that is very close to the Sun, for example. But in general relativity, if an object has a very, very small angular momentum, it'll just get sucked into the interior of the solution. You'll zoom off to R equals 0. Now, when we turn to the study of black hole physics, we will ask what happens as you get sucked into the part of the geometry where R is very small. But that is something that I will defer to our discussion of black hole physics. And now I would like to go into a more detailed discussion of the experimental tests of general relativity. And in particular, what I would like to do is use the effective potential that I have derived above to study some of the quantitative effects of general relativity on the orbits of objects in the solar system. Before I do so, let me just pause and see if there are any questions. Yes?
When Einstein calculated the precession due to general relativity of Mercury,
Yes.
he didn't, it's my understanding that he didn't use the Schwarzschild solution.
He did not use the Schwarzschild solution. He calculated perturbative corrections around the Newtonian solution. We haven't looked at, so as I mentioned earlier, one of the best ways of studying general relativity is in an approximation scheme. So he used an approximation scheme working around flat space. Okay, but now I'm going to go ahead and compute the precession of the perihelion of Mercury for you. So we're going to do it in a more highfalutin way, I suppose. Well, not particularly. We're going to use the same effective potential that Einstein used, of course. He derived it not by studying the exact Schwarzschild solution, but only by working in an approximation scheme around flat space. But the answer that he got was the correct one, of course, the same one. I suppose his argument in principle would have not been able to rule out other terms which are even more highly suppressed as a function of R, but I don't know. I haven't actually read his original paper. That's a good question. Okay. So what we would now like to study is the precession of the perihelion of Mercury. If you don't know what the word perihelion is, don't worry. I'll explain it to you in a few minutes. So our goal is to solve the equation of motion, which we wrote down above, 1/2 r dot squared plus v effective is equal to a constant, which I called E hat, where v effective is the usual 1 over r term plus the 1 over r squared correction coming from the angular momentum barrier minus the 1 over r cubed term, which is the relativistic correction. Now, this differential equation is a complicated nonlinear equation, and it is actually quite difficult to solve it explicitly, although it can be solved for, at least implicitly, in terms of some special functions. Instead, what I wish to do is I wish to treat this third term as a small perturbation and work in the approximation where the orbit is approximately given by the Newtonian orbit, that is obtained by neglecting the relativistic correction, and then including only that final relativistic correction as a perturbative expansion, and only computing the first correction in that perturbation series. And, of course, the relativistic corrections for the orbits of planets are absolutely tiny, so this will turn out to be a rather good approximation. But the point is that general relativity leads to a qualitatively new fact. So orbits in Newtonian gravity are closed, whereas in Einstein gravity, orbits are not closed. And so that means that even though this perturbation is small, it leads to an effect which is observable. It will lead to the fact that orbits are not closed. Okay, everyone ready? Roll up your sleeves. We have a little more work to do today before we can derive the precession of the perihelion of Mercury. So, in fact, I hope you remember the analogous discussion in the case of Keplerian gravity and the motion of the planets in Newtonian gravity, because the tricks that I'm about to use are identical to those that are used in the derivation of Kepler's laws in Newtonian mechanics. So the first thing that I would like to do is, instead of using r as a function of lambda, where lambda was just the proper time along the geodesic, I would instead like to study r as a function of phi rather than lambda. Now, phi is a monotonic function of lambda, so of course I could use phi as my dependent variable instead of lambda. How are they related? Well, phi dot is L squared over R squared. So that means that dr by d phi, which I will just call R prime, is related to R dot in the following way. That is just using the chain rule equal to R dot over phi dot, which is R dot times r squared over L squared. So what is the equation of motion in terms of r prime rather than r dot? Well, I just have 1/2 r dot squared, which is 1/2 r to the 4th, 1/2 L to the 4th over r squared. Wait, there's no square there. You guys need to keep correcting me when I make mistakes like that. So it's 1/2 L squared over r to the 4th times r dot squared plus V effective, which is minus r over 2r plus L squared over 2r squared minus r L squared over 2r cubed. Sorry, r prime squared. Is that what you were saying? Yeah. Okay, so that doesn't appear to make life any simpler. But I will now make a second simplification. So, well, first, let's just make this a little simpler by multiplying through by 2r squared over L squared. So what do we get? We get 2r squared over L squared E hat is equal to r prime over r squared minus r over L squared plus 1 minus r over r. The second trick that I would like to use is to take as my dependent variable, instead of the radius, I will take 1 over the radius. This is a rather famous trick in the Kepler problem, and it's the same trick that I'm going to use here. So I will let u be 1 over the radius, and just to make my life simple, I'll take it to be a constant times 1 over the radius, where this constant 2L squared over r has been chosen for my future convenience. So in particular, what does this kinetic term r prime over r look like? Well, that is just r prime over r is minus u prime over u. You lost video. Oh, okay, good. Okay, good. So u is a constant over r, so u prime over u is just minus r prime over r. So rewriting this equation, what do we have? We have E hat times 2 over L squared R squared, and R is 2L squared over R times 1 over U. So the left-hand side of this equation is going to be 1 over U squared times 8 E hat L squared over R squared. And that will be equal to U prime over U squared minus two over U, coming from this term, just plugging it in here, plus 1 minus R squared over 2L squared times U. Or multiplying through by U squared, what do we get? We get U prime squared minus 2U plus U squared minus r squared over 2l squared times u cubed is equal to a constant. Okay. In order to understand this differential equation a little bit better, let's take the derivative of this with respect to phi again and divide by 2u prime. So what does this become? This becomes u double prime. Then taking the derivative of the second term gives me a u prime, and dividing by 2u prime gives me minus 1, plus u, because that's 2u prime, then dividing by 2u prime, minus r squared over 2l squared, and the derivative of u cubed is 3u prime u squared, divided by 2u prime, so that gives me 3/2 u squared will be equal to 0. Or, rewriting this, u double prime plus u is equal to 1 plus r squared over 2l squared. Let's collect all the terms there. Plus 3r squared over 4l squared times u squared. So let's stare at this equation for a few minutes. What is the left-hand side of this equation? The left-hand side is the equation of motion of a simple harmonic oscillator. All of physics is that subset of human experience which can be reduced to harmonic oscillators. The left-hand side has been reduced to physics, namely a harmonic oscillator. And what is the right-hand side? Well, the right-hand side can be thought of as a driving term for that harmonic oscillator. So the first term, 1, is the term that arises if you just consider Newtonian gravity. And that second term, the 3r squared over 4l squared, is the correction term from general relativity. So the first three terms are the Newtonian terms, and this third term is the GR correction. So let's go ahead and expand this in order by order in perturbation theory around the solution to the Newtonian equations of motion. So do you guys all remember from your discussions of the Kepler problem in mechanics that the Kepler problem is in fact the equation for a driven harmonic oscillator? If you don't, we have just derived it again, but it is perhaps worth reminding yourselves of this. So in Newtonian gravity, the equation of motion for the effective potential of a particle in 1 over r squared force, central force, is reduced to that of a simple harmonic oscillator with the driving term. That 1 there is the driving term. And so if we wish to expand around the Newtonian solution, that means that we need to take u to be a Newtonian solution, plus some first-order correction that I'll call u1, plus higher terms in the perturbation expansion that we will neglect. Where u naught here is a solution to the Newtonian equation, u double prime plus u is equal to 1. So what is the solution to this equation? Well, this is the equation for a simple harmonic oscillator with a driving force equal to 1. So what is the solution to that? Well, the solution to that is the solution to a simple harmonic oscillator, namely a sine or a cosine. I'll just choose my constants of motion so that it is a cosine. And then we need to add to that a particular solution of the driven equation. And if you look at the driving term 1, well, a simple solution to u double prime plus u equals 1 is u equals 1. So that is the solution to the Newtonian equation. And if you go through the whole rigmarole of remembering that u is equal to 1 over r, this is the equation for an ellipse. So this is the equation for the elliptical orbit of Newtonian gravity. And how do we go ahead and solve for u1? Well, the left-hand side of this equation is linear, so we can just expand to next order in our perturbation expansion to get a differential equation for u1. And that will be determined by the driving term on the right-hand side. Excuse me. That will be determined by the driving term on the right-hand side, where we just plug into u0 for this general relativistic correction. So that will be equal to 3r squared over 4l squared times u0 squared. Is that clear? I'm just viewing the equation. So the full equation of motion in general relativity is some horrifying nonlinear equation, which is very hard to understand precisely. So I'm just approximating it as a conic section, an ellipse, plus a small correction. And that small correction is determined by solving this equation with, on the right-hand side, the ellipse taken as the driving term. And of course that will be incorrect because there'll be some correction u2 where I take u1 in for the driving term on my right-hand side, but that will be a much, much smaller correction even than the u1 correction I'm computing now. So this is the differential equation for a simple harmonic oscillator with a driving force. So how do you solve the differential equation for a harmonic oscillator with a driving term? Well, there are many ways of solving this differential equation. My favorite way of solving a differential equation is to stare at it and guess the answer. But my second favorite way of solving a differential equation like this is to use the method of Green's functions. So let's go ahead and use the method of Green's functions. So in order to use the method of Green's functions, we just remember that the Green's function for the simple harmonic oscillator is a sine. That is the response of the harmonic oscillator to a delta function source. And then the full solution is found by integrating that delta function source by viewing the right-hand side over here as the sum of a bunch of delta function sources, which means that we need to integrate the Green's function times the driving force, 3r squared over 4l squared, times u0 squared. So we need to integrate d phi of the Green's function sine of phi minus phi naught, phi minus phi prime, times the driving term 1 plus e cosine phi prime. So that's just some integral expression. Now, I don't get paid enough to do integrals like this in real time, so let me just tell you what the answer is. You go ahead and plug this into Mathematica or, I don't know, look it up in Gradstein and Rizhik. And what do you get? Well, you get a bunch of sines and cosines. So you get a bunch of terms which oscillate in phi. Those terms don't concern us because those will not accumulate orbit by orbit. those will just lead to deviations in the orbit, which will still lead to some closed orbit. But there's one term which is the term that is linear in E, which is not periodic in phi, and which goes like phi sine phi. So there are a bunch of oscillating terms plus one term that grows linearly in phi. So this will be a deviation from a circular orbit which grows linearly in phi. So it grows each time Mercury will go through one orbit around the Sun. And this is a term which will accumulate over the centuries, over the millennia, to give you something which even a 19th century astronomer can observe. So what is U? So U is equal to U naught, which was 1 plus E cosine phi. And then the first correction term is E times 3R squared over 4L squared phi sine phi, plus terms which we're going to neglect because they just oscillate. And now, I would like to notice that this parameter that appears here, this E times R squared over 4L squared, is very, very small. So I can approximate this as 1 plus E times cosine of 1 minus alpha times phi, where alpha is equal to 3 R squared over 4L squared. So I'm using the fact that if you look at cosine of 1 minus alpha phi, then for very small values of alpha, this is cosine phi plus alpha phi sine phi plus terms that are higher order in alpha. So what does this mean? This means that U is periodic, but it is periodic with a period that is slightly less than 2 pi. Remember, phi is the angular coordinate. When phi goes to phi plus 2 pi, we come back to the same place we started from. And initially, U was 1 plus E cosine phi, and cosine phi is periodic with period 2 pi, so that meant that the orbit was closed. Now, U is approximately given by something which is periodic, but periodic not with angle 2 pi, but with angle 2 pi over 1 minus alpha. So the orbit is not closed. And instead, we pick up an angle, delta phi, which is 2 pi times alpha, which is about 3 pi over 2 R squared over L squared per orbit. So this is the famous precession of the orbit of Mercury. So for example, if you compute this for Mercury, this is about 43 seconds of arc per century. This is an observably large quantity, and indeed it was observed in the 19th century and explained by Einstein in the beginning of the 20th century, and it is the first success of general relativity. And it is the first and one of the most powerful pieces of experimental evidence for the theory of general relativity. This is really a moment to step back and bask in the glory of what we have done. Let's take a minute to think about where we started. We started by thinking about the equivalence principle, by thinking about geometry, about how to formulate laws of physics in curved space-time, by using the principle of coordinate invariance, and then writing down the only possible equation that we could write down, which was consistent with those principles, which was Einstein's equation of general relativity. We then solve this. We find that it's almost exactly given by Newton's laws, plus some small correction. And the correction that we compute turns out to be something that has been around for 15 years. Well, it was around in Einstein's time for 50 years, and is an outstanding mystery in physics, which has now been explained. I think that the history, actually, of the precession of the perihelion of Mercury is rather interesting. So, by the way, perihelion just is a name for the point in the orbit which is farthest from the sun. So the precession of the perihelion just means that the axes of the elliptic orbit are changing with respect to time. And, in fact, if you actually look at the actual precession of the perihelion of the orbit of Mercury, it's in fact much bigger than 43 arcseconds per century. It's about 10 times bigger. It's an order of magnitude larger. Now, so in fact, in the 19th century, this was a mystery, but it was not a huge mystery, because remember, the fact that orbits are conic sections is a consequence of the two-body problem, but there are other planets in the solar system which will have small but noticeable effects on the orbits of the planets. So, for example, it was a favorite pastime of the 19th century astronomer to calculate the effect of Jupiter's mass on the orbit of Mercury, and to realize that, wow, that's pretty big. It's a few hundred arcseconds per century, and that explains a large amount of the precession of the perihelion. And then you can go and repeat this same computation for all of the other planets. And what these 19th century physicists and astronomers found was that the three-body effects from all of the other planets in the solar system accounted for all but 43 arcseconds per century of the precession of the perihelion of Mercury. So when I say that this general relativistic effect can be observed, that's true, but you need to be very careful to account for all of the other effects which would alter the orbit of Mercury, including those from other planets. So for a very long time, in fact, it was believed that the additional 43 arcseconds per century was not due to the fact that Newtonian gravity was incorrect, but was rather due to the fact that there was another planet that we hadn't discovered. Now, this anomaly was present only for Mercury and not for the other planets, and so that meant that the planet needed to be very close to Mercury, and in particular it needed to be closer to the orbit of the Sun than Mercury. So astronomers spent a great deal of time and energy trying to find such a planet. They even came up for a name for it. They called it Vulcan, because the algorithm is to name planets after gods, and Vulcan was the god of the underworld, he was the god of forging and fire and stuff like that, and it was a very hot planet. So astronomers spent a long time looking for the planet Vulcan, and they couldn't find it, and that was the outstanding mystery. And it turns out that the resolution of this mystery was not something so mundane as the existence of another planet, but was in fact due to the fact that Newtonian gravity was incorrect. And in fact, relativistic corrections proportional to 1 over the speed of light squared, are in fact observable in the orbit of Mercury. So that is the end of our story today. We'll continue next class with other discussions of experimental tests of general relativity.